Okay, so let's do our first lesson of our new unit. I'll just sit from here if that's okay. This unit's on electromagnetic radiation, and this one is really a logical extension of what we just finished. We just finished a unit that was all about three main types of forces, three main types of fields. We've got gravitational fields, we've got magnetic fields, we've got electric fields. And what some scientists were discovering in, I think, the 1800s, give or take, was that there was a link between two of them. Gravity kind of stands on its own, but magnets and electricity, there is a direct overlap between them to the point that we can actually create electricity or we can create a magnet, right? Remember how I would draw that three, let's draw it up here again actually, that three triangle kind of diagram there? Where if you have a magnetic field or an electric field, or I should leave more room, or if you have some motion, if you have two out of the three, you can make the third. Like for example, we can make a motor. A motor requires electricity and magnets, and you can make a motor run. Or if you have the motion of electrons, you can make an electromagnet. Okay. So we're starting with a little bit of history, but scientists are basically coming together and discovering that electro and magnets, they're one and the same. And around the same time, scientists were also starting to discover one of the, probably the most influential technological advances that we use nowadays. They were discovering the electromagnetic spectrum. And that's where I want to begin. Have you guys heard of the electromagnetic spectrum at some point before? It's in the grade 8 curriculum, so I know that's been a while. But are you guys familiar with the idea of like radio waves, microwaves, infrared radiation, all the way up to gamma rays? Is that a familiar concept? The reason why I say this is so influential is that we use this all the time in the 21st century. And so our current technology, and what I'm really getting at is this concept here. Anything that's wireless is really based on our ability to harness specifically radio and microwaves. We can't see them, right? If you guys know much about the spectrum, visible light is the only type of radiation that we can actually visibly see, but we use microwaves and radio waves in walkie-talkies and ham radios, and now we use them. Bluetooth is basically microwave technology, right? Anytime that we send a signal, the fact that I'm even writing on my little writing board right now, that my microphone is sending a signal, is all due to discoveries made about 200 years ago in the field of electromagnetic radiation. And it really builds on this idea of electricity and magnets can not only work together, but we can actually use them to send out a signal. Let me use that word as well, a signal. Now, sometimes these signals are safe. Like radio waves and microwaves, they're very safe. Sometimes the radiation that comes off really isn't in the form of a signal. It's like X-rays or gamma radiation. And anything on this side of the spectrum over here is often quite dangerous. We're going to learn why over the course of the unit, but the short version is that it has too much energy. And because it has too much energy, often these things cause cancer. Do you guys know what UV radiation causes for cancer? Yeah, skin cancer is usually the most common type of cancer that gets caused by UV radiation. Anyone ever been to the dentist before and you have to like put on the big lead vest, right? That's to prevent cancer. Gamma radiation is actually used for people who are undergoing chemo, who are actually trying to kill cancer cells. But I mean, there's huge effects of that, right? Like you're quite sick, your hair falls out. So everything on this side of the spectrum over here is generally quite dangerous. Everything over here on this side of the spectrum over here, we use it to send signals. Infrared, by the way, do you guys know what sort of device runs off of an infrared that we use to send signals? Television remotes are one of the first ones that started using infrared in order to send a signal, right? If you have a television remote and you have like the little sensor that's inside of it, it would use IR technology. So, okay, why don't I get going here on my actual notes here? So we're now talking about electromagnetic radiation. And before I get into the electromagnetic part in more details, I need to make sure you guys are familiar with this concept. It travels at the speed of light. Is that something that you guys learned back in Physics 20? Do you guys know this formula here? V equals frequency times wavelength. Is that a familiar formula? this is known as the universal wave equation. And yeah, let me even write that out. This is the universal wave equation. And what physicists discovered is that anything that is some sort of wave, it fits this pattern. There is a frequency that a wave has, and if you guys know much about frequency is how often something occurs. So if it happens every second, it's not quite as frequent as if it happens every 10 minutes, right? Frequency is measured in a unit called hertz, Hz. Okay. Wavelength is like how far apart the wave is spaced, and this diagram right here is a good way of describing that. Radio waves have a very long wavelength because they have a very long distance between when they go like up and back down again, whereas gamma radiation has a very short wavelength. What I really need to make sure you guys are familiar with, though, is that the velocity of anything that's in the EMR spectrum, speed of light, 3 times 10 to the 8. Is that familiar? Do I need to spend more time on that? Okay, I'll move on. Okay. This is something we're going to need to work with then. Okay. Scientists started to realize that the electromagnetic spectrum was actually being caused by magnets and electricity. If you're wondering, like, Chris, how does my cell phone send a signal to a tower? How is my thing right here sending a signal? I'm going to get to that in a bit, but it's magnets and electricity, right? Through electromagnetism, we can actually create these signals. I need you guys to know the order, okay? I have seen diploma questions in the past where they basically ask you to know the spectrum. So you should know that radio, micro, and infrared are the 3 that are the long waves. Visible is usually in the middle. It's the stuff we can see, obviously. And then ultraviolet, red, gamma are your high energy, low wavelength side. If this helps at all, you should also know that the colors in the visible spectrum go red, orange, yellow, green, blue, indigo, violet. Because you need to know that like red backs on to infrared and violet backs on to ultraviolet. Okay, you have to make sure you get the colors of the light spectrum right as well. Okay, so let's talk about what scientists were discovering basically 250 years ago, 200 years ago, give or take. Scientists were discovering that they could create EMR. And one of the first electromagnetic waves that was sent purposefully was by a guy named Heinrich Hertz. And I'm going to talk about him on future slides as well as show you a quick video. But what Heinrich Hertz discovered is that he was actually able to send a wireless signal. And I'm going to use that terminology a lot because we use that now. He didn't know it at the time, but he was sending a radio wave. And he was messing around with magnets, he was messing around with electricity, and he discovered that as he did some stuff over here with magnets and electricity, so with a magnetic field, oh goodness, what am I doing, Chris? Ignore that, let's try again. By having an electric field and a magnetic field over here, he was messing around with those. He discovered that his apparatus way the heck over here also had electric and magnetic fields happening. And he didn't expect that. And so that's what I want to discuss here, is that we've now recognized that electromagnetic radiation is always due to an accelerating charge. I want to bold this and point this out for a second. Accelerating charges. You guys recall that triangle I drew a little while back, right? The one with electric, magnetic, and motion. Okay. If you have an accelerating charge, you have 2 of the 3, don't you? Because if you have an accelerated charge, the charge itself has an electric field. And if you are accelerating it, it means that it's in motion. So therefore you have 2 out of the 3. We discovered that that is actually the cause of EMR. And here's the reason why. You guys remember the first hand rule? The first hand rule basically said that if you have a wire and you run electricity through the wire in this direction here, that according to your hand rule, I'm going to try to draw my thumb here. Here's my thumb. And then here's your fingers, kind of like this. How's that for a hand? Is that my left hand rule? Can you guys kind of see that there? This is your first hand rule here. It means that what we're doing is we're making a magnetic field in a circle around this. There's a circular magnetic field around this wire. Well, what we now recognize is that when those electrons were accelerating, it was making a changing magnetic field. But that changing magnetic field then caused a changing electric field. And that changing electric field caused a changing magnetic field. There's kind of like a chain reaction going on here. Okay. A moving charge makes a magnetic field. But if you move a magnet, remember how moving a magnet and a wire made electricity? So what ends up happening is this big loop. An electric field makes a magnetic field. But then the magnetic field makes an electric field. But the electric field makes a magnetic field. It makes a series of alternating fields where right here, you're now making an electric field. But that electric field over here makes a magnetic field in like a different direction or dimension. You know how you have your X, your Y, and your Z dimensions? This is what scientists were discovering, is that they were making alternating fields. Yeah? It's not actually increasing and decreasing. This is our visual representation of what we think is happening, because Physics 20. I guess this is where I didn't teach you guys this. Did you guys ever use slinkies or like some sort of manipulatives in Physics 20 and literally make a wave go back and forth, right? Where it goes back and forth. Those are mechanical waves. If you ever see like an ocean wave go up and down, you can actually see it physically go up and down. Those are mechanical waves where something is actually moving. Well, there's not something actually moving here, okay? But as the best way for us to visualize what's happening, we think of it like a mechanical wave where there's a wave going up and down. But is the electric field, is there actually something going up and down? Well, no. Does that make sense there? This is our visualization of what's occurring. So let me kind of back up a little bit here and talk about the scientists we need to know here. Ørsted discovered that if you run a current in a wire, like I was just showing you a few seconds ago here, running a current in a wire makes a magnetic field. But Faraday proved that if you have a wire in a magnetic field, it makes a current. Can you see how we have a loop here? A current can make a magnetic field, but then a magnetic field makes a current. So then a current makes a magnetic field, and a magnetic field makes a current, and a current makes a magnetic field, and a magnetic field makes a current. And it basically makes this continuous forever loop. And all of a sudden, scientists were discovering we're actually making what we now call radiation. I'll use the word a signal because they weren't making the dangerous kind of radiation. Like usually when we think of radiation, we're thinking of gamma and X-rays. But basically they were making a signal. And Maxwell, basically, what is this, 250 years ago? No, even less than that, 150 years ago, finally put this all together and realized that there's something going on here. And he had a 6-point theory that he had. Here's basically what he suggested. You can make electromagnetic radiation whenever you have a charge that is accelerating. As long as you have a moving, accelerating charge, it's going to make EMR. Here's why again. A charge that's accelerating will then make a magnetic field. But we know that a magnetic field with something moving will then make a current, which is basically an electric field. But then the electric field will then remake a magnetic field. And so if I can go back to that picture right here, what ends up happening is this electric field right here, it creates this magnetic field here. But this magnetic field right here creates this electric field down here, which then creates this magnetic one, which creates this electric one. Which, you see how it's self-propelling? Yeah. It's hard to visualize though, because like I was saying to Sean, there is nothing to see, right? Like what does a wireless signal look like? There's nothing to see. And one more thought here. Does a wireless signal need like air or like an atmosphere to travel through? No. We can send these signals through the vacuum of space. They are not mechanical waves that actually move particles. So this is really just our representation of what we think they look like based on what we know mechanical waves do. We just assume mechanical waves behave like all other waves. So anyways, let me get back to Maxwell's concepts here. He then figures you make EMR from accelerating a charge and the loop begins. He also believed that the frequency that a charge moves with is going to match the frequency of the EMR. So if you have a charge that's accelerating, often as we're accelerating it, we're actually making it go back and forth and hopping across like a gap. We actually make it go back and forth. Maybe I should find you the picture of Hertz's experiment for a second here. Let's go to this one here. This was, to my knowledge, the first radio signal ever sent. It was Heinrich Hertz, and he was trying to prove Maxwell's theory. What he essentially did is he set up a rig right here where a spark was being sent back and forth between two plates. You guys remember alternating current? The fact that you can actually make something go one way and then go back the other way and then go back and forth again? They basically used alternating current here to make an electron zap back and forth across a small little gap. Think of it like a spark plug, only rather than jumping once, it's jumping back and forth. As it oscillated back and forth at a certain frequency, he discovered that he could actually send a signal that was getting picked up by another ring over here. And so as a spark was getting sent back and forth right here, he discovered a spark going back and forth in this ring right here. I think I may as well show you my YouTube video clip on this, actually. Why don't I do that now? Bear with me, because I think I'm going to lose you if I don't show you this clip next. Oh, where did I leave it? Oh, there it was. Okay, here's a short video clip on Heinrich Hertz's experiment.
Around 1880, the brilliant scientist James Clerk Maxwell developed the mathematical theory of electromagnetism. His theory predicts that electromagnetic waves propagate through space at the speed of light. Many other scientists of the time were trying to prove experimentally the existence of these waves. In 1887, Heinrich Hertz, a German physicist, designed a series of brilliant experiments to demonstrate Maxwell's hypothesis. Heinrich's equipment was simple: a spark generator coupled to an antenna and a metallic ring set at some distance apart. Heinrich proposed that the electromagnetic waves generated at the antenna will travel through space, and if Maxwell's theory was correct, they would induce a current in the ring.
Okay, so I'm just going to pause right here. Here's basically the cliff notes of what Hertz's experiment was in 1887. He set it up so that right here he was going to run a current, so an electron was going to jump back and forth. Basically you have an oscillating electron, and I'm still making my cursor go back and forth on purpose here. There's an oscillating electron back and forth. As the electron moves back and forth, you have two out of the three, right? You have motion, and you have an electric charge. And what that did is it makes a magnetic field. And so, for example, blue right here could be the magnetic field. But as the magnetic field changed, because it went back and forth, changing magnetic fields create electric fields. And so that could then be the red wave that gets formed. Again, keep in mind, there's nothing actually moving here. This is just kind of our visual representation of there's an electric signal being sent out in one color, there's a magnetic signal being sent out, and one makes the other. Electricity makes magnetism, which then makes electricity, which then makes magnetism, which then makes and I can do that forever, right? Now, here's what he set up, though. Over here, he has an oscillating electron, and over here, he has a ring. And the ring has the exact same gap over here that he started with over here. So there's like a gap here of, like, say, 5 millimeters. There's a gap over here of 5 millimeters. And what he discovers is that by the time this electromagnetic wave hits over here, the electromagnetic wave hits this wire right here, and it causes electrons in this wire to then zap back and forth over here. And so he sent the first signal over here. This signal caused electron motion to cause electron motion over here. So I'll let the video play a bit more.
Will appear in the ring gap. In this video, we make a simplified version of this famous experiment. This project requires a high voltage pulse in order to work, and we will obtain that pulse with a lighter like this. Here we have one that we have modified for our purposes. Let's open the lighter. Here it is. This is a piezoelectric element that produces a pulse of several thousand volts. There are these two wires that come from the piezoelectric, and we have connected a
Okay, I just want to pause for a second here. I don't know if you guys know this, but a lighter actually has a fairly high amount of voltage inside of this one right here. What does a voltage do again? What is the definition of voltage? Change in what? Change in energy. Yeah, right? I mean, if you know your formula, it's V equals change in energy over charge, right? If you've got a lighter right here, how is a lighter going to get something to light? Well, you're going to have to zap an electron across a field here, right? And that's going to then change some energy. It's going to make a spark, and the spark will then make the lighter fluid light, right? But in order to push electrons across a spark plug gap, you need quite a high voltage. So that's why this guy right here is going to modify a lighter so that he can get a decent amount of voltage by pulling on the trigger. And then I'll let the video keep playing. I know he's got quite the accent here. Can you guys see that? So right in between the two of them there, right, as he pulls the trigger, this is what's happening inside of a lighter, is that electrons are jumping across a gap. So let's walk this through again. If electrons are in motion and accelerating, they've now made a magnetic field. If I could put a magnet or a compass nearby, I would see my compass needle get deflected. But like, there's really nothing to see. But really, that wave concept of something going up and down in 3 dimensions, in every single dimension, a magnetic wave is being sent out. But as the magnetic wave builds itself, it's also changing. And so the magnetic wave rebuilds a new electric wave, which rebuilds a new magnetic wave. And I'm going to say this a lot today. It self-propels itself, which is super cool. Okay, maybe I should pause here. So you can see what's going to occur here is that this guy's now set up so that over here, he's got this set up right here. There's going to be a little spark gap right here, right? And he set up some antenna so that it hopefully sends the signal just a little bit better, just like, your old school satellite antenna kind of traps the signal a little bit better. It's hopefully going to send it. Over here, there are no wires between apparatus A and apparatus B. But if we're going to zoom in on this little spot right here, as the spark goes in between these 2 spots right here, we're going to see a spark show over here. Guys, that's what's happening in every single little wireless device we have. Because if you ever wondered, and maybe you've never cared, but if you wonder, how does your cell phone send a signal between one place to the next? How does my Bluetooth receiver do that? That's what it's doing. It's sending out a little itty-bitty electromagnetic wave. And so as the electrons jump between spots right here, it sets out a magnetic wave, which sends out an electric wave, and eventually gets picked up over here and causes this to have electrons move. That's a signal. So anyways, let me keep the video going.
To replicate Hertz's experiment, we have the spark generator connected to these 2 wires, and the electromagnetic waves will travel through the receiving antenna. Here we have a neon lamp connected to the antenna, and when the spark is produced here, the neon lamp will glow.
I forgot. So he didn't actually just have the spark between the 2 of them. He put a little lamp right there, because if you can kind of imagine this, if there's going to be a spark between these 2 gaps right here, that's going to be the motion of electrons, right? Well, we've created a circuit then, because if it's able to jump across this gap, it will then go through this loop and back around again. You've now made yourself a closed loop. Except it wasn't a closed loop. There is literally a gap right here, and that gap is going to get filled by the electrons jumping from one side to the other. And the only reason they're jumping from one side to the other is a wave caused them to do that. A magnetic wave caused electrons to move. That magnetic wave came from an electric wave, which came from a magnetic wave, which came and go back to here, which came from this one here. This, I can't understate this enough. This has changed our world. The fact that we now understand how to utilize waves, things that we can't see, the things we do with them now are incredible. And in 1887, they were only just figuring it out. So anyways, let me keep the experiment going and then we'll move on. So you guys are going to have to look real close right here at the lamp. Can you see that? Right there? And you can see the jump right there. And you can see the lamp glow there too, hey? Isn't that amazing? This is just a homemade apparatus. You'll see a bolt right there and the lamp right there, hopefully. Can't see the lightning. There it was. You see that one? And it causes... So I know I'm repeating myself like 8 times, Sorry, I'm really redundant, but this is that important. So one more time, what's happening? We're shooting electrons across here. We have accelerating charges. We have 2 out of the 3. We have motion in our electric field. Motion in electric field creates a magnetic field. But our magnetic field started with nothing, right? There literally was no magnetic field. Now there is one. So therefore, our magnetic field is going from nothing to something. Therefore, you now have a changing magnetic field. Well, as soon as you have the motion, a change in a magnetic field, it recauses a change in your electric field, which recauses the magnet, which recauses the electric, which recauses the magnet. And then way over here, the magnetic field over here causes an electric field, and it actually causes the electrons to jump from, say, a negative to a positive side right here. As they jump from the negative to the positive side right here, they fill out a loop, and the lamp gets lit. Now, this is a pretty basic concept, but if I could then go back to where my notes were now. Just give me a sec to get loaded up again here. I think now I can explain better as to what's happening here. So this is what Heinrich Hertz was doing. Over here, he had that same little gap, but he didn't shoot it once, okay? He was actually oscillating the electrons back and forth across the spark gap, back and forth. And as it oscillated back and forth, that's a frequency. That frequency then showed up in his gap right here, and basically, it was like the first radio receiver, where the oscillating electrons right here sent out a wave. The wave gets picked up over here, and it gets transmitted. Okay, I should go through some of my notes here. I think I left off here, and I kind of ignored some of this. So let me go back to this slide here for a second, if I could. This is what Maxwell theorized. If you look at the dates, by the way, Maxwell put together his theory in 1865. Heinrich Hertz didn't do his experiment until 1887. I don't know whether your previous physics teachers have talked to you a lot about experimental and theoretical physics, but Maxwell was doing theoretical physics. He had a theory about how he thought electromagnetic radiation should work, but he wasn't confirmed until 22 years later when Heinrich Hertz was able to experimentally demonstrate it, which I think is really cool. So anyways, here's the rest of his theory that he came up with, and he was right. So he thought, 1, EMR gets produced whenever a charge is accelerated. 2, the frequency with which that charge moves is going to match the frequency of EMR produced. 3, EMR goes the speed of light. 4, why is this even happening in the first place? There are electronic and magnetic fields, and they are perpendicular to each other. Can we see them? No. Do they even require a medium to move through? No. It's not like this is a mechanical wave, like when I'm talking. Do you guys know that like when I'm talking, I'm sending out a wave as well? But the wave from when I'm talking is literally causing air particles to compress and expand. Did you guys learn that in Physics 20? Okay, maybe I should review that another day. But like there are some waves that actually involve the actual motion of particles, like a sound wave or a wave in like a water pool. These waves right here, they require no medium to move. And so although we talk about them being perpendicular to each other, it's not like we can actually see them or test them. It's the best explanation we have. We're going to get to this later on in our unit, but they discovered then that EMR behaves like all other waves, which means they can do things like refract and interfere with each other. And I've got a lesson for each of those as we go through our unit. The final thing Maxwell predicted, the universal wave equation applies to EMR. So, does anybody have any questions that they can think of right now? This is kind of a deep topic here. Anyone have anything that they want to ask? Guys, are you okay back there? You're just kind of chatting away, so can I move on? Okay, these were actually Maxwell's 4 equations. And you don't need to know them. They're not on any formula sheet. However, I would like to point something out for any of you guys who are in calculus. What is this notation? Do you guys? That's a derivative, yeah. Yeah, this is the derivative of a magnetic field with respect to time. Yeah. This would be the rate at which the magnetic field is changing. Yeah. Now, you guys aren't going to do any of the calculus, but in case you're wondering, that's where the overlap comes in. Yeah. This would have been the rate at which the magnetic field was changing over time. Yeah, the overlap there. Okay, let's move on. Okay, I've got another video here. I'm going to change gears now. Now that we've talked a bit about magnetic waves being sent out and we have a little bit of an understanding where they came from, I need to shift gears and talk about how scientists discovered the speed of light. Because you guys were probably told the speed of light is 3 times 10 to the 8. But I'm not sure that maybe you were taught, well, how do we know that? And so what I need to do over the next few slides is describe how in the universal wave equation, the velocity that we know to be 3 times 10 to the 8, how that was discovered. So I have another short little YouTube video. Again, it's not like that professional, but we'll watch this one first, then we'll pause and talk about it. So this is my video on measuring the speed of light.
Let there be light. Assuming you are sitting in a normal-sized classroom, it took that light about 10 nanoseconds to reach you. In turn, for you to have known that the light has reached you, it took about 200 milliseconds. Congratulations, you were about 20 million times slower. As you can see, the speed of light is so...
Did you guys catch that? Yeah. Here, listen to that again here.
Light. Assuming you are sitting in a normal-sized classroom, it took that light about 10 nanoseconds to reach you. In turn, for you to have known that the light has reached you, it took about 200 milliseconds. Congratulations, you were about 20 million times slower.
Okay. Light travels so fast that our brain is magnitude slower. Our brains work pretty quickly. Like when I see something occur, my brain recognizes it. And yet light is that fast. It happens basically instantaneously. And yet it's not instantaneously. Light actually has to travel through a medium. And you guys remember that visible light is one of the forms of EMR, and it's the only form of EMR that we actually have the ability to perceive. Okay? I cannot perceive X-rays. I have no ability to feel them. I can't feel a radio wave. By the way, you guys are being bombarded right now with radio waves and microwaves. If you have a cell phone anywhere nearby you, a signal is constantly being sent out, right? And so there are all sorts of waves bouncing through this classroom. You don't feel any of them. But light is also a wave. Light I can see. And yet, my brain doesn't even go nearly as fast as light itself travels. So what this video is going to talk about as we keep going forward here is how scientists tried to measure the speed of light.
As you can see, the speed of light is so fast that it precedes our immediate perception. So how do people measure it? More specifically, how do people before the 20th century try to measure it? Did they get close to the real answer? During Galileo's time, many believed that the speed of light was infinite. In fact, they had no reason not to believe that. Galileo, being Galileo, disagreed. He tried an experiment in which he and another person each took a sharp lantern and walked a mile apart. The rule was that as soon as one of them flashed his lantern, the other would flash back. And Galileo simply divided the distance by time.
Okay, so Galileo is the first person we've heard of who tried to measure the speed of light. And if you can kind of imagine this scenario here, from what I understand from the legend, he had a whole bunch of lanterns on top of mountains. These are all on top of mountains right here. And he apparently knew the distance from one to the other, right? And what the person would do is this person right here would turn on their lantern. And as soon as this person right here turned on their lantern, then this person right here, as soon as they could see it, they would turn on this lantern here. As soon as this person turned on theirs and this person over here could see it, they'd turn on theirs. And in theory, you'd have a whole bunch of lanterns all of a sudden getting turned on as soon as you could see the next one there, right? Then you would measure how long it took for the last person to turn on their lantern. So if it took like 1 second, 2 seconds, 3 seconds, you'd say, okay, it took 3 seconds for us to all flash our lanterns. And then they'd take the total distance traveled and divide by that time, and you'd have a speed of light. What's the flaw in this experiment? Human error, yeah. The immediate second that you see this light show up, are you going to actually be able to flick the lantern on? No, right? And we already know that your brain doesn't even travel nearly as fast as light travels. So
He found that the speed of light was actually 10 times greater than the speed of sound, or 3.4 kilometers per second. Little did they know, they did more to measure the reaction time and the speed of their arms. Galileo had less success in measuring the speed of light than he had in avoiding trouble with the Catholic Church. During the 1670s, inspired by Galileo's discovery of Jupiter's moons and his belief in the finite speed of light, Danish astronomer
rover, then another attempt to simulate the speed of light. Eventually, rover was trying to predict the orbital planet's exposure to Io. To his frustration, however, he discovered that Io was not working strictly on schedule. Rover simply did not accept the possibility that Zeus might have been keeping Io's rates from the telescopes. He noticed that Io was ahead of schedule when the Earth was close to Jupiter and behind schedule when Earth was farther away from Jupiter. Rover deduced that the irregularities in Io's orbit must have been due to the finite speed of light. Based on careful observations, his data implied the speed of light was about 300,000 kilometers per second. In France, 1849, Louis Fizeau produced another measurement of the speed of light. Fizeau showed a beam of light through a rapidly rotating tube wheel into a mirror 5 miles away. The mirror reflected the same beam of light back to the rotating wheel. By varying the wheel's rotational speed, Fizeau could see when exactly the light was not enough time to be reflected back to the same gap in the wheel.
This is one of the first experiments that actually did a pretty good job of trying to test the speed of light. If you can understand what's happening here, you shoot some light from here, and I'm sorry that the thing's on top of it now, but you shoot some light from here at this mirror. It's actually like a two-way kind of mirror because it either allows it to reflect or go through. So half the light will actually go through, half of it will bend, and it bent this way through the mirror. But you see how there's this rotating thing right here with teeth on it? Well, that means that like half the time light gets through, the other half it doesn't. So it's almost like flicking the lights on, off, on, off, on, off, on, off. Can you imagine that? But it just depends on how fast you rotate this particular wheel. If you rotate it really quick, you're basically going to have light go through here, bounce back through, and through again. And as he changed the rotation of the wheel as well as this distance right here, sometimes the light would be able to go through here, through there, and back again before the next tooth on the gears right here got in the way. Does that make sense? So if it goes from here, through a gap, all the way there, and back again before the tooth gets in the next way, then you can pick this up on the sensor over here. But if you set it too far or too close, this mirror, or you change the rotational speed too much, what ends up happening is the light will go through, it'll go through one of the teeth, it'll go all the way here, and when it comes back again, it's too late because this thing is rotated just enough to block the light again. Right? And so by playing around with this, he was able to figure out the speed of light. Why don't I show you that one more time again? Okay. I don't know that you noticed that, but he said that this was 5 miles away. If light had to go from me to the other side of the classroom and back, I don't care how fast this disc is rotating. Light is going to go from here to there and back, and it's going to get through that tooth gap right there. There's no way you're going to block it. But what if light has to travel 5 miles that way and 5 miles back? Now it's actually traveling a reasonable distance. You get what I'm saying here? And so if light has to travel 5 miles this way and 5 miles back, we might actually be able to make the teeth on this thing go fast enough to then block that light, and therefore we wouldn't be able to see it. But when we do see it, then we can actually measure that speed of light.
This speed of light is about 313,300 kilometers per second. In France, 1862, Beyond Foucault modified Fizeau's experiment and made a more accurate measurement of 299,796 kilometers per second. The actual value of the speed of light is 299,792.458 kilometers per second. There are a number of different ways to measure the speed of light now. One of them is remarkably similar to Galileo's method. Astronauts put a mirror on the moon, and when a laser on Earth shoots the mirror, our atomic clocks can find very accurate times related to travel there and back, which is about 2.5 seconds. So remember, next time you Google the speed of light, give a second to silent tribute to the people that work so hard to make their life just a bit easier.
Okay, so that's actually what I want to talk about next, is that speed of light that gets used in the universal wave equation. Bear with me while I load this guy back up again here. the speed of light that gets used in this universal wave equation, scientists at the exact same time that we're trying to figure out how EMR works, they were trying to figure out, well, what is the speed of light going to be? And so basically the problem is, how do we have ability to have the light travel a certain distance in a certain amount of time? Because if we can do velocity as distance over time, we can measure the speed of light. The problem is, how do we accurately measure a distance? How do we accurately measure time? So this video showed you a couple of ideas, like Galileo's lantern idea, the rotating teeth idea. But the modern idea is actually, where's my video here? Do I not have my video? It's the Big Bang Theory video. Here it is. I'm going to do this one right here. If you've ever seen the TV show Big Bang Theory, they actually do this experiment. What you do is you shoot a laser from Earth at the moon. And when Apollo 11 went up back in 1969, they put a reflective surface on the moon. So what ends up happening is light goes all the way from Earth, hits the reflective surface on the moon, and comes back to you again. That is actually a decent amount of distance for it to travel. And since the distance is so big, it actually gives us enough time to properly measure the time amount. Using atomic clocks, what you effectively do is do the distance to the moon, there and back, divide by time, and that's how we solve for the velocity. So I'm going to show you one more video clip. This is the Big Bang Theory TV show, and yeah, they basically were doing the experiment that now modern scientists do. Moon laser experiment.
Is my friend back?
Hey, hello. Whoa, is that the laser? Bitch. In 1917, when Albert Einstein established the theoretical
I can't see that all that well.
laser and his figures are quantum theory their strong room, his fondest hope was that the resulting device can be mission accomplished. Let me explain what we're doing here. In 1969, the astronauts on Apollo
Hope that's better.
positioned reflectors on a surface of the moon in order to shoot a laser off one of them to let the light bounce back through this sort of artifact.
Very cool.
One question. How can we share what we're on? The laser? The moon. See, now, this is a man who can... That's a great question, Zach. No, it's not.
Sheldon, my guy.
It's not a great question. How could somebody possibly think we're going to blow up the moon? That's a great question. Don't worry about the moon. We set our lasers done. We'll be able to see the beam when it leaves, but it won't be strong enough when it comes back to you and let it go. Idiot. Funny. That wasn't there. We'll measure the photons at the turn, and then see on this computer what gives us a back. Cool to be 3D. Aliens will fire a laser at the moon, they would say. There's this way. 2.5 seconds to the right contact. That's the moon.
So there's more to the clip, but that's really the essence of it. It's not exactly the most exciting experiment in the world, right? You shoot a laser at the moon. The laser doesn't blow up the moon because the laser is just light, right? It's just concentrated light. It's, you know, fairly strong in terms of its intensity. You can see the green laser, right? Shoot the laser at the moon. It bounces. It reflects off the surface of the moon, comes back again. If you want to calculate the speed of light, you just need to know two things. How far is it to the moon? We know that amount. You need to know how long it takes. Here's the thing. If I want to figure out how long it takes for light to get from here to there, it happens in a millisecond. We can't measure that properly. But if light is actually traveling from Earth to the moon and back, it takes long enough now that we can actually measure it with our measuring devices because it's 2.5 seconds. So take the distance to the moon times by 2, divide by about 2.5 seconds, now you've got a speed of light. Does that make sense? So that's how a modern experiment would then calculate the speed of light. I've got a few more things I need to get to. I need to pick up the pace here, actually, because I think I'm going too slow for us to finish. This is another very famous experiment I need you guys to know. This is called the Michelson experiment. And he actually managed to do something very similar to the moon experiment. And he did it very accurately. It's not quite as good as laser to the moon. But in 1848, 1846, I don't know, again, it's like 200, 150 years ago now, right? He managed to figure out how to measure the speed of light using a rotating octagonal mirror. So let me see what I can try to describe what's happening here. What he did is he sent some light from the top of Mount Wilson, and he then shot it off of a mirror down to a second mirror, back up to the exact same mirror. This is a little complicated. It's quite the process. So light comes from Mount Wilson. It goes down 35 kilometers because he needed to travel an actual decent amount of distance. Does that make sense? If it doesn't travel at least a long ways, you can't measure this well enough. So it goes off this side of the mirror, down to the curved mirror, back up to this mirror, and he measures it. Okay. Now, if he can see the light in his telescope, that's good. Because what he did is he made this mirror rotate. Just like the teeth that were on the other guy's experiment, the teeth that were kind of inside there. As the mirror rotates, here's what's supposed to happen. Light's supposed to hit this surface. The mirror is going to continue to rotate. And what has to happen is this side right here has to get to right here by the time the light has gone all the way down and all the way back up. Because otherwise, the mirror won't be back in its set position. It'll be kind of slightly off-center. And if the mirror is, say, like slightly out instead, what would happen is light would bounce off this, it would come down, come back here, and it would bounce that way. And then you'd get no reading in your telescope. So it has to be calibrated just perfectly so that it does one perfect rotation. I'm going to just erase this stuff here. So hopefully I'm explaining this well enough. But light has to come in from Mount Wilson, hit this edge right here. It has to go there and back. In the time that it's gone there and back, this edge right here has to be perfectly now in this spot right here. If it's slightly ahead or slightly behind, the light's not going to bounce at the right angles. Does that make sense? And so if he can set this up, then he sees light in his telescope. Now here's how the math worked out. He was then able to measure the frequency of his wheel spinning. Because he could measure that, right? He has the ability to measure the frequency of his wheel. He measured it to be 533 hertz. He then took the reciprocal of his frequency, 533 hertz, and he found a speed, a time basically, a time value. That is the amount of time that it took for this wheel to have one face right here rotate to just the very next spot. So it actually didn't do a full rotation, it only did one rotation. So what he then did is he divided that by 8. He took his time value and divided by 8. Because his frequency was for the wheel to go all the way around, he doesn't need the wheel to do a full rotation, he needs it to do 1/8 of a rotation. So he took his time value and divided by 8. Final step, he now knows how long it took for light to basically go all the way down and all the way back. Now, there's a little bit of an error here, because the light was actually traveling on kind of a hypotenuse. But he knew how tall Mount Wilson was. It was 35 kilometers. So that meant light basically went 35 kilometers down, 35 kilometers up. Except it wasn't exactly 35 kilometers. You get what I'm saying here? Because 35 kilometers is what would the adjacent side of a triangle would be. And light was actually traveling on a bit of a hypotenuse. But if it's traveling 35 kilometers, it's really not that big of a calibration error. So long story short, 35 kilometers times by 2 gives you 70 kilometers. That's this number right here. 7 times 10 to the 4 was 70 kilometers. So he then knew light had then traveled 70 kilometers there and back, and it did so in this amount of time, and therefore he calculated the speed of light. And this is the first speed of light calculation I know of that is like super precise, super accurate. All the rest of the ones that we've talked about were like in the ballpark, but they all had some sort of measurement error. Like even the guy with the teeth, and you know how the teeth were rotating in the wheel? That still wasn't perfect because it depends on how big the gap was. The gap wasn't like infinitely small, the gap had a bit of range to it. This was like the best experiment ever. I need to point something out for you guys. It's very likely you're going to be asked a Michelson experiment question on the diploma. This is a very common question type. And so what they usually do is they give you the speed of light, because we now know the speed of light, and they ask you what frequency would the wheel have to rotate at. So there's always 3 formulas we use in concert. One is the formula where period is 1 over frequency to get time. One is just a made-up formula. You have to divide by 1/8 because the whole wheel is rotating in this amount of time, but you don't need the whole wheel to rotate. You just need it to rotate one section, exactly one section, not too far, not too little. And once you have your time value, you do distance divided by time. It's effectively this formula here. It's the formula V equals d over t. Uniform motion. So, anybody have any questions they can think of regarding speed of light calculations? My opening topic, by the way, this first topic in our unit, is kind of a hodgepodge of random stuff. If you feel like I'm kind of jumping around, it's because I am. We're not really ready to like focus on any one topic in particular. What we're really doing is bringing together 100+ years worth of scientists' contributions and kind of talking about them one at a time. So I began talking about Maxwell's contributions to electromagnetic radiation theory. I've now moved on to discussing the speed of light contributions. Now I want to discuss how we detect electromagnetic radiation. So here's kind of the next topic here. We know that there are some properties of EMR that we can measure. One of the ways that we can measure is like directly. If a signal is sent between two items, we can actually see it because EMR is just directly unimpeded. That's literally what's happening when you see stuff, right? A light is traveling off of an object into your eyes. It's directly going to you. You can see it. But there's also indirect methods. For example, reflection, like on the moon example we just saw, right? You can actually reflect EMR off of different substances. Where do I want to go with this? I'm gonna fast forward ahead. I'm gonna kind of go in different orders here. Scientists before the 1800s, we're talking back around the time of Sir Isaac Newton, they were really debating what light was. So I'm kind of on to like another random subtopic here. I'm kind of hopping around. Sir Isaac Newton thought that light was a particle, and he had good reason for it. He believed that light was a particle for these reasons. He thought it was a particle because it always traveled in straight lines. If you were to shine a flashlight on something, the flashlight always goes in a linear direction. A flashlight doesn't just all of a sudden bend around a corner. It goes in one spot. Light can be reflected. Light can bounce off of a mirror. Well, if light was like a particle, then particles, they would bounce. He also thought that light must be a particle because if it traveled through a vacuum, how else is it going to get to Earth? He knew light was coming from the sun, but there's no particles between here and the sun for light to like move through. So he thought it was a particle. But then all of a sudden, new scientists come along and suggest, hang on, maybe light is actually part of, I'm just fast forwarding back to the very, very first slide. Scientists start to say, well, hang on, maybe light is part of the electromagnetic spectrum, and it behaves more like a wave, waves which go up and down and have amplitudes and frequencies and periods. And so there was a huge debate in the scientific community for years. Is light a particle, or is light more like a wave? Where am I going to go with this one here? Okay, so here's some evidence that Newton had for light being like a particle. Newton was literally like the most influential scientist of his time. Basically, if Sir Isaac Newton agreed with you, you were right. And if Sir Isaac Newton disagreed with you, your work was garbage. And so there was no scientist that was willing to challenge Newton on his particle model until he died. And then after Newton died, some scientists were then brave enough to suggest, okay, maybe light doesn't always behave as like a particle. What if it has wave properties? And here's a few different scientists who had evidence that light was more like a wave. Francesco Grimaldi proved that light could actually diffract through openings. Do you guys know what diffract means? Okay. I need to do a bit of a mini lesson here. There are a few things that we know that waves can do. One is that they can reflect. If I bounce a wave off of a mirror, it can go in like this and bounce off. Reflection would be a good example of particles. Particles reflect. Things can also refract. Refraction is where a wave or particle or something is coming in this direction, and it changes its trajectory. When you wear glasses or contact lenses, refraction is occurring, where light is bending off of its normal trajectory into a new spot. Okay, that's refraction. Diffraction would be more like this. Imagine that you had a wall, and over here you sent out some wave fronts of water. Okay. What would happen is some of those waves would then hit the wall right here, and they would then start bouncing back the other way. But since the wall ended right here, what's going to happen to these waves over here? Well, they're going to keep going because they were unimpeded. What diffraction means is that slowly but surely, they're going to spread out a little bit more. I didn't draw that one very well. Diffraction means that all of a sudden you're going to see a wave sitting over here, and you're going to think, well, hang on, wasn't the wall in the way? Wouldn't this have been blocked? But it slowly but surely spreads out in what's called a wave front. I didn't teach you guys Physics 20, but maybe you saw or heard of examples of like a wave front before as a way of describing how waves work. If not, I'm going to teach you this later in the course. Long story short, because I'm running out of time here, I got to pick things up here. Grimaldi managed to prove that light could diffract, and diffraction was a wave property. Here's another cool story. A guy named Simeon Poisson, he predicted that light should not be able to refract. And eventually, this guy here, Dominique Arago, he actually managed to prove that light diffracted, and he named it after his buddy to basically like, how would I describe this? This is basically like eternally throwing shade at somebody. Because like, first guy says, there's no way this works. Second guy discovers it works. And rather than naming it after himself, like most scientists do, he named it after his friend to like bug him about the fact that he was wrong. So anyways, here's how diffraction works. What the guy did is he sent light out around an object. And you guys will recognize shadows, right? If you shoot light out and there's something in the way, there's going to be a big shadow over here on the other side. But this is really cool. What ends up happening is when light goes past this object, remember how I showed you diffraction? Diffraction will eventually cause a wave to eventually bend its way around. And if it can bend its way around on both sides, both sets of light will actually recombine. And this makes no sense whatsoever unless light is a wave. But you can actually see a little section of light showing up dead center in the middle of your shadow. Because what ended up happening is this wave front, as it got blocked right here it got blocked, but as it went around, it slowly but surely re-spread itself back out again, this wave front right here, and eventually it recombined over here. So, okay, I need to wrap things up because I'm running out of time here. What scientists then discovered is this, and I love this photo right here. We are going to build towards this in our next 5 to 6 lessons. Scientists were struggling to figure out, is light like a particle where it bounces off of things, or is light like a wave? And we're going to now end, I'm doing huge foreshadowing here, but our last topic, topic 7, is going to wrap all of our previous middle topics up. We're going to talk about wave-particle duality and the idea of quantum states. And this broke physics. It really did. Because the answer to the question, is light behaving as a wave or a particle? The answer is yes. It's behaving as both. Light sometimes acts like a particle, and it bounces off of things. Light sometimes acts as a wave and refracts or diffracts through things. So can you guys see the optical illusion in this thing right here? Can you see how it says P-A-R-T-I-C-L-E? Behaves as a particle, but it also behaves as a wave. Can you see the optical illusion there? Okay. This is what we're going to build towards. Over the next 6 lessons, I'm going to do some topics where we're going to discuss properties of electromagnetic radiation. Tomorrow we're going to talk about reflection. Reflection would be evidence that light is a particle because reflection is things that bounce. But then the next day we're going to talk about refraction. Light has the ability to bend. That's more like a wave property. We're going to talk about diffraction and interference. Then we're going to talk about what really broke physics. It's called the quantum concept. It's called the photoelectric effect. And we're going to discuss how, for the longest time, scientists thought light was a particle. Then they thought light was a wave. And they were like, no, light is a wave. Isaac Newton, you were wrong. And then someone discovered that light is a particle. And then someone discovered that light actually does both at the same time. And I don't expect this to make sense because I have to teach you all of the individual steps. But my intro lesson is basically going to bookend with my outro lesson. Today, what I hopefully told you is a bunch of theory that scientists had, and then we're going to finish off and wrap it up and discuss that, like, EMR. Has anybody ever heard of the word photon? It's not just like a made-up pretend Star Trek word. We actually believe that light exists in little photon packets. So that's where we're going to go. Okay, I'm going to wrap this up here. Here's the last set of slides here. I have a few slides here that discuss... this is where we're basically going. It wasn't until 1900 that Max Planck discovered photons. You don't really need to pay too much attention to this because I'm going to teach this later. But you can read this on your own if you'd like. Here's my last slides. I need you guys to know a little bit about the electromagnetic spectrum then, because that's what we're going to focus on. You need to know about radio waves. You need to know about microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, even cosmic rays. I'm not going to read through my slides because I hate when teachers just say stuff that you can read. But here's what we hopefully accomplished today, because I think I'm now done basically all my notes. Okay. We talked about some scientific contributions to EMR. Maxwell's equations, we talked about the Heinrich-Hertz experiment. Scientists were working on that, trying to puzzle together how does EMR work. At the same time, scientists were trying to figure out how fast does light travel. And eventually scientists realized that EMR and light are one and the same thing. And so it's like a puzzle where all the pieces were starting to come together at different points during time. Okay. So we talked about that. We also talked a bit about where we're going to go. Properties of EMR. Is light a wave? Is light a particle? Does it bounce off things? Does it phase through things? Or does it do both? And then my last slides here are just some properties of EMR. So I'm going to shut up now. Here's what we're going to do the next few days. The next couple of days, I'm going to take one lesson each day, and we're going to talk about a property of light or a property of EMR. How it refracts, how it reflects, how it interferes, how it diffracts. And we're going to discuss all of that. And then we're going to wrap our unit up with talking about how it does all of these things sometimes at the same time. So, if it feels like you learned nothing today, I'd understand. Because it's kind of a hodgepodge, my intro lesson. It's just a little of everything. Okay? So there is nothing to be assessed on out of this lesson, by the way. This really is like an intro lesson. Okay? So last thought. I do have assignments posted, and you can start looking at those if you like, but honestly, you can't do anything until I teach you a few more lessons. So don't worry about doing any new assignments, but can you guys finish up the old assignments that you need to do in your past unit? So anyone who hasn't handed in a lab or assignment 3, can you get that to me ASAP? Okay. Guys, that's all I've got. You guys can take off if you like, because it's basically 5 minutes till the bell. If you have questions, let me know, okay? I covered basically what I wanted to.